Yeah?
Okay. Welcome, everyone. I will just introduce you to Valerio for this very interesting talk on clone detection. I think everyone should be interested. So I just leave the expert explaining how it works. And the speech will be 45 minutes, then 10 minutes at the end. If you have questions, just take notes, and then we will go through the question at the end. Thank you.
Okay, thank you. Thank you for the introduction, for the interesting. And thank you everybody for being here. The topic of the talk today is clone detection in Python. So let's start by thinking about duplicated code. As you all know, Martin Fowler, the author of the book In the Picture, did a list of the so-called bad smells in the code. And number one is, in the stink parade, is the duplicated code. He said that if you see the same code structure in more than one place, you can be sure that your program will be better if you find a way to unify them. But anyway, we're all Python programmers, so we know the Zen in Python, and in particular, we know that the Zen stated that there should be one, and preferably only one, obvious way to do it. So we're done. We should have no problem about clones or duplications. But anyway, let's see these two classes. They're being extracted from the tree.py file from the NLTK project, Natural Language Toolkit project. These two classes are these are complete classes. So, and they're in the same file but two different classes. I think that you already get that the code is quite the same. But if you want details about it, let's see that. Only this part is different, this part, regarding the superclass, this part, this one, and the last one. And the last part is a little bit different because prob equals to 1 and here 1.0, but it's quite the same. So, a lot of duplication. Duplicated code is a real problem. Researchers in the field of software maintenance stated that in large systems, from 5% to 30% of the code is similar. And in extreme cases, even up to the 50%. That was the case of a COBOL system, payroll. And they also said that duplication often occur in development for time pressures due to upcoming deadline or to overcome limitations of the programming language. Anyway, from my point of view, there are three public enemies to combat. The copy, paste, and modify. So, let's start by talking about the clone detection. I'm going to give you a brief introduction to what is the problem of clones and what is about. And then we will see some details about the clone detection in Python, in the sense that we will see clones in the Python code, and to anticipate something, the last couple of slides I will show you some duplication in the CPython implementation, and I hope that we will have something to discuss about. Anyway, so what are called clones? The most cited definition about clones states that software clones are segments of code that are similar according to some definition of similarity. Well, it's quite general. But likely to me, researchers racked their brain and define it a sort of classification. First of all, we have to say that there can be different definition of similarity based on the program text and based on semantics. So, two different groups. But actually, there are 4 different types of clones in literature. Okay, so let me give you an example. This is the original one, the first one. And we consider this fragment of code, this simple function in Python, as the original fragment. This function takes a file path and input, a markup parameter that has this default value, and then what it does is to read the file and check if if the lines in the file ends with the input marker, and if so, it adds the lines to a list, and then it returns the list. So, quite trivial. Anyway, so, type 1 clone, exact copy. Identical code segments except for difference in layout, white space, and comments. So, that was the example. This is the original fragment, and this is the clone. So, a new line here, different comments, but the code is exactly the same. Type 2 clones, so-called parameter substituted clones. And in fact, the two guys here are quite similar, but with some differences. The structural identical segments except for difference in identifiers, literals, layout, white space, and comments. Let me give you an example. This is the original one. This is the type 2 clone. I modified these variables, parameters, the name of the variables, comments, somewhere, and it is. But the code is structurally the same, but has a difference in name of variables. This is the main concept. Then, the type 3 clones. So, quite the same, but this guy has something more. Anyway, so the idea is to similar segments with further modifications, such as changed, added, or deleted statements, in addition to variations in identifiers, literals, layout, comments, or blah blah. So, due to lack of space, I didn't repeat the original fragment, but you know well now. And if you remember, this fragment does quite the same thing, something more. In particular, it checks if the input path corresponds to the file, for instance. If not, it returns known. And in addition, instead of returning only lines that ends with a marker, it also returns lines that do not end with the input marker. Yeah, that's quite a sort of little variation of the behavior. In particular, yeah, the differences have been added here, here, and here. And finally, the last one, the so-called semantic clone, catch the idea that two fragments of code are do exactly the same operations, but are different, but are implemented in a completely different way. So, back to the example. This function does exactly the same things of the original one. In particular, it read lines one shot with read lines instead of reading line by line, and then uses the filter function instead of checking each line while reading. But the output of the two functions is exactly the same, as you agree. So, what could be the consequences of clones? Well, the question now is, do clones increase the maintenance effort? Researchers do not agree on the answer to this question, but they agree on the fact that for large systems, there is a large consensus on the fact that clones should be detected, at least. The point is, imagine that you have to do a sort of impact analysis. You have to do a modification on your system, and you have to analyze how much does the modification will cost to you. And you have to know which is the part of the system affected by such modification. So if you know that some parts of the systems are duplicated, you may better estimate the effort. But anyway, the hypothesis about the maintenance effects, consequences of clones, are that code clones increase code size. But in general, if you have to fix a bug in your system, you should fix all the same bug in all the replicated version. However, everything that does not come for free. It's not always possible to remove clones. So, in general, you may think about, well, if I have two different functions with subparts that are shared between them, I may apply, anyway, extract method, for instance. I may extract the common part in another function, another method, and then remove the clone. This is not the general rule. It depends. The removal of clones is hard if variations exist, in particular if there are the so-called type 3 clones. Anyway, actually there are plenty of clone detection tools. And such tools may be classified according to the specific kind of similarity and the specific kind of information they exploit in detecting clones, code clones. The first group is the so-called text-based tools. So these tools get the source code and compare lines line by line. So they perform a textual detection, a textual comparison. On the other hand, there are the so-called token-based tools, which are a little bit more efficient in the sense that they do not compare strings, raw strings, but they compare token sequences. Going on, there are syntax-based tools. Such tools exploits the syntactic information gathered, for instance, from AST, the abstract syntax tree. And the last group is the graph-based tools. So they try to identify graph or subgraphs similar between code fragments. We may talk about a little bit more to graph-based tools later. But the idea is to exploit the so-called PDG, so the program dependence graph. They usually apply the... Well, so what happened? Okay. Okay. So, clone detection techniques. Any technique, as you may imagine, has its advantage and its disadvantages. The string token-based techniques are the ones that run very fast and run faster, but they produce too many false positives. In particular, since they're based on string comparison, they have no information about the syntactic structure. So, for instance, they may take clones that correspond to the end of the function and the beginning of another function, because they have no information about the syntactic structure of the code. For such tools, the code is plain text. On the other hand, syntax-based tools are well suited to detect structural similarity, but not so suited to detect type 3 clones. So different structure with such type of clones. And the last set of tools, the graph-based ones, are the only one able to deal with type 4 clones, so the so-called semantic clones, but they have a lot of performance issues. Anyway, so, which is the idea? Is to try to combine different sorts of information. And the way I did it was using machine learning techniques. The idea in my case was to combine structural information gathered, for instance, from AST or PDG, so trees or graphs, combine them to lexical information, so the program text. And the way to combine them was to exploit the so-called kernel methods for structured data. I'm not going to give you a lot of details, and likely for you in any mathematical demonstration or proof of their correctness, of their soundness, but if you trust me, such techniques are well grounded and on solid mathematic backgrounds. And the basic idea is that for structured data, the similarity of such objects could be expressed in terms of, recursively, in terms of their constituent parts. So basically the idea is to define a way, if you have a structured object, such as a tree or a graph, try to find a way to compare the similarity of each node, and then find a way to replicate the computation, the comparison among the overall structure, and you're done. This is the basic idea. Actually, there are some properties, some mathematical properties that have to be guaranteed in order to be a kernel function, but anyway, in general, this is the basic idea. And for instance, there are the so-called tree kernels and graph kernels. So what I need to define a new kernel for structured data? Well, I have to define a set of features to annotate each part of the object. So I have to identify which is the most relevant information for me when I compare the constituent part of the object. So the base of the recursion, if I can explain it better. And then, when I'm done, I have to define a kernel function to measure the similarity on the smallest part of the object, for instance, nodes for STS graph, exploiting such features. And finally, I have to define a kernel function to apply the computation on the different subparts of the structured objects. Let me give you an example. This is what I did for kernel methods applied to, oh sorry, this is a typo. This is not the PDG but the AST. So this is a node of the ST, so it is a tree, not a graph. And I defined a set of 4 features for each node. In particular, I said that each node in the ST has the first feature, which is the instruction class. So each node refers to an instruction in the code, as you know, and this feature identifies which is the class of the instruction it refers to. For instance, if this is node refers to a for loop, it is the root of for subtree. The instruction class for this node is loop, a general loop. The instruction feature, instead, tells that this node is not a general loop, it is a for loop. Then, another feature is the context. If you think about the overall tree structure, the context says that it is the instruction class of the closer statement node. I mean, I may use a for loop inside another for loop. I may use a for loop inside a call function, inside an if statement, so they make difference. And the context tries to catch exactly this idea. Finally, lexemes, and this is the lexical information use it in combination of the structure once. The lexemes are the lexical information gathered recursively from leaf nodes. And finally, I have to compare the all subtrees, and this is the only math I introduced in the slides, so forgive me. And I aim at identifying the maximum isomorphic subtrees. So given two subtrees referring to two different blocks in the code, I want to identify which is the most subtree that contains similarities gathered from the both fragments. Yeah, this is the general idea. Well, so this concludes the first part, so the part on clone detection. But now let's think about what is more interesting for us, the clone detection in Python. Well, this is the sketch of the overall process. Clone detection in Python, for me now in this presentation, has two different meanings. The first one is that I implemented the clone detection tool in Python, and I compared my results with another Python clone detection tool. And the other meaning, the other one is, what about the clones presence in the Python implementation? I mean in the CPython code. We have some preliminary results about it, and I want to share them with you today. So the general analysis process encompasses 4 different steps. The first one is the preprocessing. Basically, giving the set of all files, I have to pick the different source files I'm interested into. In this case, Python files. Then I have to process such files in order to extract the different subtrees, so the syntactic trees, and then I have to derive the computation in order to compare all such trees. And finally, the last step is to aggregate the results. So once I identify different clones, I have to pull them together, aggregate them, and finally, I should also add a sort of label on such clones saying which is the type of the clones. Because some clone detections tools do it, some not, but it is informative to know not only that 2 fragments of clones may be clones, but also which type of clones they are. Okay, so this is the overall sketch. I'm gonna give you a little bit details about the detection part, which is interesting for us. It is based on MPI4Py, but the general idea is that in the detection process, what we have to do is to compute the similarity matrix. Similarity matrix means that in each entry of the matrix, there is the similarity between the fragment I to the fragment J. And this is a triangular matrix because it is symmetric. So kernel function must be symmetric in order to be a similarity. Because if I compare an object with another one, the similarity value should be exactly the same if I reverse the order. That's the idea of symmetric. So I have, in the overall detection process, I have to compute the similarity matrix, which is a process that could be easily parallelizable. We did this by using MPI4Py, but for instance, another idea should be to exploit different parallel algorithms such as MapReduce, for instance. We think to port the implementation to the cloud, trying to exploit the Google App Engine implementation of MapReduce, for instance. Anyway, this is an interesting part. Sorry. This is an interesting part because MPI4Py, for me, is quite an elegant library of function. It basically represents a wrapping of MPI libraries implemented in C++ and usually present in computational machines. So if you have Python installed and MPI libraries, you may easily use such a module. It is based on the idea that you may run different processes, and among such processes, there is one process which is the process coordinator, which have to coordinate every process in the sense that it waits for all processes to terminate. And this is how all works. So the idea in the computation of the similarity matrix in parallel is we divided the matrix in blocks and then in chunks in order to make them more efficient, because you have to consider that the main drawback of the MPI for Pi is that it does not support any mechanism to share memory, in the sense that it works on sharing memory completely. You have no control on giving to different process different data structure. In fact, the coordinator process has a method that calls that is so-called broadcast method, which is a method that distributes among different processes the same data structure. So you have to pay attention on how to handle the memory, because if you think, for instance, at the usage of memory, you may have some issues in analyzing even medium-sized systems, because methods, the number of methods, if you analyze each method of a system, becomes higher and higher. So the memory issues is not a simple problem. You have to deal with it carefully. So anyway, let me present you some empirical evaluation we did, as I mentioned before, on the comparison with another tool, which is Clone Digger. I hope many of you have heard about it. It has been the first clone detector for Python and in Python. So I mean the first clone detector that was able to analyze Python code, and it was presented for the first time at EuroPython 2006. We compared with such a system which is ST-based, pure ST-based, and we compared the performance of the two systems on a system with randomly seeded clones. So we randomly seeded clones in a system, and we compare our performance in how many clones we detected, thank you, and how accurate were our results. In particular, on type 1 and type 2 clones, so the exact copy and the structure parameter substituted clones, we got the same results, exactly the same. So this was sort of proof of the ability of ST-based techniques in getting all the type 1, in detecting all type 1 and type 2 clones. But for type 3 clones, we got different results, the blue ones. In particular, to measure the different results, we used the so-called precision recall plot. In particular, precision and recall are two different measures well known in information retrieval or machine learning field. They try to answer to two different questions that are quite complementary, in the sense that the precision tries to understand how accurate are the obtained results. So alternatively, in other words, how many errors do our results contain? On the other hand, recall tries to catch the completeness of the results, in the sense that how many clones have been retrieved with respect to the total number of clones. So, as you may imagine, if you have high precision, so you are accurate enough, you have a low recall, because you return few results. High precision means that you are accurate in your results. So if you have a high precision, has blah blah here, these are in particular the different similarity thresholds we considered. At similarity 0.98, we have precision that was 1. So every clones we detected was a real clone, but it constitutes only the less than the 50%, the 20% of the total number of clones. So how can I deal with it? Well, the idea is to combine these two measures in the so-called F1 measure, which is basically the harmonic mean of the two. So when I have to measure the performance of my system, I look at the mean between the harmonic mean between precision and recall. And this is, the yellow ones are the F1 measure. So this was a story. Another story was this one. Is Python less clone prone? Some researchers try to investigate this claim that maybe scripting language, such as Python, so-called scripting language, may be less clone prone, in the sense that if you have an elegant way to write the code, write the same code into different languages, but in Python it's much more smaller, maybe you may produce less clones. Well, these are the results they got on different systems. There were, I hope you may read it, but Python systems were Eric, NetworkX, Zope, Eric plugin, Plone, Moin, and Sconce. But I don't know what Sconce is. Anyway. Oh, sorry? Oh, okay, thank you. So it's a versioning system. Thank you very much. Thank you. Thank you. And, oh, sorry. And then they considered also some Java system and some C# systems. Well, my idea is that these results are not general enough to do a general claim about answering yes or no to the question, is Python less clone prone? Because systems may be considered much more systems and the same system in different version, from my point of view, to do such a claim. But anyway, what they got was that distribution of clones in Python is quite similar to the Java ones. This is, thank you. This was their claim, but is much smaller than C# one. Well, Python one is a little bit less, a little bit more small. So but it depends on the clone detectors they used, by the way, because the old story is that they used text-based clones. So recalling what I said before, the text-based clones, clone detectors, sorry, were the faster one, but the less accurate ones. So maybe this claim could not be so generalizable. Anyway, this is a result available in literature, so I'm glad to share it with you today. But anyway, I think this could be an interesting point of view. And finally, what about our results? Was clones in CPython, in particular CPython 2.5.1. This is an excerpt of, really, actually, this is not the old function, the old implementation, but this is datetime new, and this is time new. So function that you may have used quite every day. And let's try to take a look at it. And you may notice that the two fragments are quite the same. So no code, no pieces of code is reused between the two implementations. They have a lot of duplications. Well, this also happens. Yeah, I have 8 minutes, so I can tell you all the story. We are looking at this code, but the problem is there is no so-called gold standard. I mean, there is no repository that I may look at to know what are the real clones in Python implementation, how many clones there are, and so forth. So there are no results about clones in Python. So what we're doing in these days was to run our clone detectors, get the results, and analyze manually all the results. So, as you may think, the number of possible candidates is quite large. If I can give you a number, considering different similarity threshold from 1.0 to 0.96, we got almost 12,000 candidates. Many of them are false positives, so they were not real clones for our point of view, so that was a problem of our technique, but many of them were really clones. But the problem now is, I selected this function as an example, but I can give you maybe another one then regarding the implementation of the function, the tan function in the math library and tan-h. They have quite the same code. But the point is, will you really refactor that code? Refactoring that code should mean I may re-implement that function in order to get two function pointers, for instance, one for, and such two functions may contain the common path between the two implementation. But what about performances? That was the point, in my opinion. Well, on function like getEmployee, for instance, you may not have performance issue. But what about mathematical function? You have duplication of code, but you may you do not have performance issues. Yeah, that's an open question I'm looking at. And basically, this concludes my presentation. Thank you for your attention.
Okay, so any question? Okay, so first and the second.
So once you've done clone detection, what you could do when a new commit is done is to only compare the changed parts to the rest of the code base, and then that might make it, I don't know how long it takes for the clone detection to run, but that would make it faster, sort of more usable for people who actually want to practically use it to improve their code. Do you do something like that, or are you actually packaging your code for production use?
Yeah, nice question. The point is that you have to deal with a trade-off, because from my point of view, the detection of clones is performed offline. So you have the overall systems, you run the clone detection process, you got results, and you deal with results. But on the other hand, there are tools that run in real time. So some of them are included and integrated in development environment, such as Eclipse, Visual Studio. and they give you instant results. But anyway, it's a trade-off, because if you aim at getting all the clones, so in increasing the recall, so the completeness of your results, you may do not perform them online. Sorry. But if you think that few results but accurate ones are acceptable for you, you may do online during development. So it's sort of trade-off. Thank you.
How much work do you think it would be to re-implement the backend to work on ASTs from other compilers? For example, GCC has a Gimple format that is intended to be used by different tools. I think that would be something that they would really appreciate if they had a tool to actually analyze the code for various C or the Linux kernel, for instance. So would it be possible, or do I misunderstand the design?
Well, will it be possible? I think so. I never thought about it, actually. But anyway, I think it should be a good idea. I don't know about the performances from one hand, and on the other hand, the problem is always the same. Yes, we detect the applications, but not always the applications are bad. So maybe introducing such functionality in a compiler may be too restrictive. Maybe. But, well, it should be a good idea.
First two questions. First, could you please remind the annotations you are using on the nodes? So instruction, class, instruction, context, and what was the fourth one?
The fourth one was the lexical information. I mean, in the AST, you have the literals on the leaf nodes. So if the node is a leaf, lexeme is the lexical information in itself. If it is an internal node, this information from leaves is propagated to internal ones.
Thanks. And the second question about building this matrix, do I get it right that you're comparing each function with each function?
Yeah.
And if so, how deal with the situation if the whole function is cloned inside, somewhere deep inside another function? Do you detect those detections, those clones?
Yeah, well, good point. The point is that they are so-called gapped clones, in the sense that if you have to see them in this way. You have two functions, one contained in another one. That was your point, right? Okay. So, in my function, my kernel functions identifies in the similarity between the two functions the common parts. Anyway, the size of the two functions is important, because it is different that you have two identical functions from one hand, and it's different if you have one function included in another one. So the difference is in the similarity value it produces. In the first case, it produces 1.0 because it is exactly the same. In the second case, it has a value that is lower than 1 because there are some parts in one function that could be not mapped to the other one. Basically, this is the idea. Thank you.
So, in the last 25 years, pretty much everybody tried to do component programming, and it has failed more or less several times. But what is actually working now for code reuse is just this copy and change. And do you find a correlation between design patterns and the duplication of code? And is it measurable between static languages like Java or dynamic languages where the patterns are more high level?
Well, about the first question, yes, there is a correlation in the sense that the research now is going in this direction. In the last 20 years, researchers produces a lot of clone detection tools, as you already seen. But now the problem is, once I got the results, what I can do with such results? And now they're trying to understand, from one hand, which is the correlation with behaviors of developers, what are their attitudes and why they produce clones, from one hand. On the other hand, the point is there any way to exploit refactoring and design patterns to remove clones? So basically there is a correlation. For the second question about different languages and different refactoring ways, well, I have no idea about that. But, and the reason why is that researchers basically consider statically compiled, statically typed languages such as Java or C. The analysis on Python is very limited in research field, but I think it is quite interesting because they belongs to different kind of programming languages. Thank you for the question.
Okay, another question about performance. What kind of scalability does your algorithm have? Those matrices looked a bit like quadratic or worse, so what's big O notation approximately?
So performance, you mean the asymptotic notation? Yes. Well, okay, so
basically regarding the size of the project you analyze. So does it only work for toy projects, or could you, for example, analyze a Linux kernel or stuff like that?
Well, okay, so we didn't try yet to such big system, to big systems such as the Linux kernel, for instance. But on the other hand, we tried it on Python, for instance, which is not not so small. We tried it on PostgreSQL, which is a very large system, and on Apache, HTTPD. So the running times were exploiting the parallelization. For instance, on Apache, it takes half a day to perform the computation for every pair. On big systems such as Postgres, it may take some days to complete. Well, but the problem is we tried MPI4Py with only 4 processes, so a very small number, because we didn't have the availability of more cores. We tried, and moreover, but on the other hand, we tried it on a single machine, exploiting the multi-core on the same processor, not on a cluster of machines. So this could be a very interesting point to look at. Thank you.
One of the results that was quite surprising is the how often Java has copy-paste or clones, because as many people programming this in an IDE that will generate the code for them, immediately, a priori, that's a clone. And using design patterns, a priori, is an AST clone. So did these results surprise you? And after inspection, is there any more analysis that needs to be done there, or do we take it at face value and say, wow, that's surprising, but it's unintuitive, but that's interesting, I guess.
Well, please consider that Java systems are the most studied ones. And especially, I may give you this example. One of the most studied system is JHotDraw. JHotDraw is a very toy application, but from the academic point of view, it is the gold application because it is full of design patterns. It was implemented by Kent Beck, I guess, and it contains a lot of patterns. So it is the typical academic and didactic application presented during lectures, for instance. But JHodrow, which is full of patterns, is full of clones. So clones in Java are quite spread over all the projects. Some other results I got was on the, for instance, the Java Swing implementation. So GUI, graphical interfaces. Well, on that side, that was not surprising me, because if you know the structure of graphical interfaces, the design of graphical classes in Java, you may notice that there are a lot of duplications, even in the design phase. So why not in the code?
Any question? Okay, I have two questions.
Oh, thank you.
So, do you think it's possible to use similarity hashes to check
already exploited,
and adding to them to facilitate the selection of the leaf of the tree, the genetic algorithm?
Genetic algorithm, I think that they have not been exploited. But hash and on fingerprints, in basically a sort of hash implementation of the AST. That was a technique I looked at some days ago.
Yeah.
Well, see. Yeah, sorry. Yes. But on genetic algorithm, I didn't heard about.
The second one is, do you think it's possible to prepare some kind of metrics using similarity index and complexity index for the codes to see
what do you mean by complexity?
For example, which code has the deepest level of clones and which code has the most spread usage of clones?
Okay, so you say to define such a matrix in a posteriori analysis or a priori?
No, posteriori.
A posteriori, yeah. Well, yes, sure. Moreover, there is the second one, the most spreaded, in the sense that which is the fragments of code which has a lot of dependencies with other parts of the system, is an information that is given you almost for free using PDG, for instance.
Yeah.
So program dependency graph.
Yeah.
So yeah, this is this is the part I told before. So now we detected all such clones, but now what about it? So
yeah, sure.
A little bit analysis on to get a deeper understanding.
Yeah. So any question? Okay. So thank you for your speech.
Thank you. Backup. Just